Lesson 8-7, Binomial Distributions. We're not going to confuse binomial distributions with the binomial theorem from the last lesson. The binomial theorem is how to expand something like x plus 2 to the 10th. Binomial distribution is probability. Completely different, except for the names are similar. Probability distribution is a function that gives the probability of each of the possible outcomes in a probability experiment. So we're doing something, we're calculating probabilities, and we want to know all the probabilities possible of all the possible outcomes. That's a distribution. And the sum of all those probabilities should equal 1, which means something happened. So here's a probability distribution for rolling a 6-sided dice. You have a 1, and the probability of getting a 1 is 1/6, because 1 side over 6 sides. And the same thing for the 2, the 3, the 4, the 5, and the 6. And if you add those probabilities all together, you'll get 1. So to construct a probability distribution, first of all, you need to make a table of probabilities, something like this. And then make a histogram. A histogram is a bar graph. So for here, it'd be a really boring histogram. It has some mark where our probability is 1/6, so that's our p of x. And down here you have all your x's, all your options. And you make little bars for each of them. And since they all have the same probability, they're all going to be the same height. Well, pretty close anyway. All right, so let's say our spinner here is divided into 3 equal parts, 0, 1, and 2. Let x be a random variable that represents the sum when the spinner is spun twice. Make a table and draw a histogram showing the probability distribution. Well, the first thing we need to do probably is have our sample space. So on our first spin, we could get a 0, a 1, or a 2. On the second spin, I could get a 0, a 1, or a 2. Could get a 0, a 1, or a 2. A 0, a 1, or a 2. So those are my, looks like 9 possibilities. Well, I want a sum, right? So here the sum is 0. Here the sum is 1. There the sum is 2. That's the sum is 3. And there it is 4. So for our table, our options is we could get a 0, a 1, 2, 3, or 4. To get a 0 is 1 out of 9. To get a 1 is 2 out of 9. To get a 2 is 3 options out of 9. To get a 3 is 2 options out of 9. To get a 4 is 1 option out of 9. So then let's make our histogram. Remember, it's a bar graph. So I have 0, 1, 2, 3, 4 on the bottom. And I'm going to count by ninths. So maybe 1/9, 2/9, 3/9. Well, I guess that's all higher I need. All right, so the 0 goes up to 1. The 1 goes up to 2. The 2 goes up to the 3. The 3 goes up to the 2, and the 4 goes up to the 1. And there's my histogram. And you can see by looking at that, the 2 is the most likely to get, and the 0 and the 4 are the least likely to get. Why don't you try number 1? For number 1, let me help you. Your sample space is 5 1s or 3 2s or 2 3s. All right, so getting a 1 occurs half the time. Getting a 2 occurs 3/10 of the time. And getting a 3 occurs 2/10 of the time. And then just make a little histogram for that. All right, we're going to use the probability distribution in the previous slide to answer each question. So what is the most likely sum when spinning the 3-section spinner twice? So if I go back, I look, the highest bar here is the 2. So that's our most likely. What's the probability that the sum of the 2 spins is odd? Ooh, let's go back and look. So the sum is odd. That would be the 1 or the 3. So that's a total of 4 options out of the 9. So it'd be 4 out of 9, or 0.44. 4. Why don't you try number 5? Pause this while you answer it. 2 is the most likely, and part B would be 5/8. So those are just general probability distributions, but there's a special type that is actually very, very common called a binomial distribution. Binomial is called that because there's 2 outcomes, so 2 numbers, success or failure, or if you like, 0 or 1, 2 outcomes. We have independent trials, so it's done multiple times. And the probability for success is the same for each trial. So this is like going in and taking a multiple choice quiz with absolutely no clue about it. Each option, or each question has 4 options. So you do the first question, so you get it right or you get it wrong. Then you go to the next question, you get it right or you get it wrong. And each question is completely independent. And as long as they have the same number of options, the probability for success for guessing the correct answer is the same. So that's an example of a binomial distribution. Flipping a coin multiple times or whatever. The probability of k number of successes is nck, p to the k, 1 minus p to the n minus k. So n is the number of trials. K is the number of successes, the number of times you want to get it correct. And P is the probability of success. This 1 minus P then is the probability of failure. So this is all the different combinations, so our combinations, and then our success and our failures. So all the different successes we get times all the different failures that we get. All right, let's calculate the probability of flipping a coin 20 times and getting exactly 3 heads. Well, this is a binomial distribution because you have 2 options, a head or a tail, success or failure. Success is a head, failure would be the tail. Let's see. Our n is 20. So this would be the same coin 20 times, 20 different coins. It doesn't really matter. K is 3. Our probability of getting ahead when you flip a coin is 0.5. So it is N. Okay, the probability of K successes is NCK. P to the K, 1 minus P to the N minus K. So N is 20, K is 3, P is 0.5, K is 3. 1 minus P, which is 0.5, raised to the N minus K. And you know what's great is you can just dump that all into your calculator, get 0.00109, which is pretty low. But why don't you try number 7? Get only one head out of 20. Yeah, ain't gonna happen. Not very often. All right, at college, let's say at this certain college, 53% of the students receive financial aid. In a random group of 9 students, what's the probability that exactly 5 of them receive financial aid? Well, N would be 9 there, K would be 5, and our P would be 0.53. So it's NCK, P to the K, 1 minus P to the N minus K. So N is 9, K is 5, P is 0.53. K is 5, P is 0.53, N is 9, K is 5. And we can put that all through the calculator and end up with 0.257. So about a quarter of a 25% chance of 5 of the students receiving financial aid. All right, draw a histogram of the binomial distribution of students in example 1 and find the probability of fewer than 3 students receiving financial aid. All right, so we could make a table. So we'll have X and P of X. What is the smallest number of students who could receive financial aid? That's right, 0. And the greatest could be 9. That's right. Wow, that's 10 calculations. I don't want to do the binomial theorem 10 times. Well, you could put it in the calculator. Remember, it's NCK, P to the K, 1 minus P to the N minus K. If I put this in the calculator, I want the K to change. Maybe I'll call this K instead of X. I want the K to change. So I could put it in the calculator as Y equals N. Wait, what's N? N was 9. And I'll put the X for the K. And then P was 0.53. Put an X for the K. Then 1 minus 0.53. You'll probably need to put this in parentheses too. N was 9 and K is X. So let's grab my calculator. Go to my functions. I'm going to add a function. And what it'll be. All right, so I need my combination. So I'm going to my combination. N is 9. My K is X. Times 0.53 raised to the X. Times 1 minus 0.53 raised to the N, which was 9, minus X. And there we go. You think, hey, great. Well, if I go over to my table now, I can see right here. Oh, look at that. So when it's 0, I have 0.00112. For 1, I have 0.011. 1, 1, 3, 6. For the 2, I have 0.05, 1, 2, 3. For the 3, I have 0.13480. For the 4, we have 0.22801. For the 5 is 0.25712. For the 6 is 0.19330. For the 7 is 0.09342. The 8 is 0.02634. And lastly, 9 is 0.00330. And notice 10 is 0 because I can't choose 10 out of 9 people. Best I can do is choose 9 out of 9. So a handy way of putting it in the calculator. Just fill in everything except for the x replaces k. K becomes x. You put it in where you normally do your graphing, so your functions. And then we make a histogram. So we make a chart. Notice the highest is actually only 0.257. That doesn't seem very high. None of those look like they're very high probabilities. But if you add them all together, you get 1, meaning one of them happens. So there's the 0, my 1, the 2, 3, 4, the 5, the 6, the 7, the 8, and the 9. So you can see 5 is the most common. So 5 is the most likely number of students that receive financial aid. But we would like the probability that we're less than 3. So that'd be the probability of 0 plus the probability of 1 plus the probability of 2. So the 0, the 1, and the 2 gives us 0.06371. So it's about a 6% chance that fewer than 3 students receive financial aid out of those 9. So why don't you try number 11? In your school, 30% of the students attend a movie night. You ask 5 randomly chosen students whether they plan to attend the movie night. All right, so for this one, to put it in your calculator, n appears to be 5. And for the k, I'd put an x. Your probability is 0.3. And then it's n minus k. So that's why I put it in as the y equals, as your function. And I'll get a nice table. It should give you this histogram. All right, so what's the most likely? It looks like it's a 1. Probability at most to attend, so that is all those. Add those together, and you end up with 0.83692, or about 84%.